Hi guys, so this video we're going to be continuing on from the previous video where we looked at the normal distribution. And we're going to be looking at now a normal approximation. So this is used when we're dealing with a binomial distribution where the n value is too high. You'll notice that in the formula book you're given the n table, right? The values for the binomial distribution. As you should notice, the maximum n value they actually give you is 50. So when it's greater than 50, what we do is we approximate it to a normal distribution. So as you said, there's going to be two conditions for when we do approximate it. So the first one is when n is large. And as I said, that's roughly when n is going to be greater than 50, like this. The second condition has to be if p is close to 0.5. Now the reason behind this is if we have a normal distribution, we know the bell curve, right? We know that the probability either side of the mean value is 0.5, 0.5 because it's symmetrical. And so therefore that's the condition why we need the binomial p-value to be close to 0.5. If it's not close to 0.5, then we can't approximate to a normal distribution. And so if that's the case, then we can go from binomial to a normal distribution in something called a normal approximation like this. Okay, so for a binomial distribution, we know that the parameters are n and p, and for normal is mu and sigma squared. So if we can go from one to another, then we need to convert it. And the way we go by converting it is these two here. So the mean is worked out by doing n times p, and the variance is just one here, we do n times p times 1 minus p. That's how we get the parameters for the normal distribution. Right, so once we've got that, then we can actually go about finding the probabilities. But we have to remember that binomial is a discrete distribution, whereas normal is a continuous distribution. So binomial means it can only take positive integer values. The continuous means you can take any single value possible. So it can be a rational number, it can even be a negative number. So for that case, we have to do something called a continuity correction. An example of this is, say I have the probability that x is less than or equal to 28. So that's what I'm asked to find, okay? So if I was to draw a number line, so let's say 25, 26, 27, 28, 29. We are asked to find anything including 28 and down like this here, right? But this is for a binomial distribution. If we're converting to a normal one, well, technically, remember normal can be like a decimal place, right? So for a normal distribution, what we have to do is actually include any values which would then round to 28. So that would include the values x being less than 28.5, right? Because anything less than 28.5 would then round down to 28 if we had to round it. This is known as continuity correction, and this needs to be done when we're doing a normal approximation. Another example, let's say we have probability that x is less than 24, okay? So my tip for you guys when you're doing this is always convert this into less than or equal to or bigger than or equal to first. So this will be x is less than or equal to 23 first. And then you want to imagine we're going to go 0.5 up or 0.5 down always. And you want to imagine I want to include this value. So if I have to include 23, then I need to convert this into probability that x is less than 23.5. If I went down to 22.5, then I will not be including 23, right? So that's like the tips I try and think in my head when I'm doing the continuity correction. Let's say I'm trying to find probability that x is greater than or equal to 5, okay? And so remember, I need to include this. So this is when I do continuity correction, it's going to be x is going to be greater than, I'm going to have to include the 5, right? So I have to go 0.5 down, not up. So this would be bigger than 4.5, like this. Let's say we have probability that x is bigger than 10 and less than or equal to 15, okay? So as I said, always convert it into equal to. So this is going to be equal to probability that x is bigger than or equal to 11 and less than or equal to 15. And then you want to do continuity correction denoted by these two squiggly lines. And imagine combining or including these values. So if I have to include 11, then I have to write it as 10.5. And if I have to include 15, then I have to write it as 15.5 like this, okay? So just always make it equal to and just imagine to yourself, I'm going to go 0.5 up or 0.5 down. Just imagine I have to include those values. Right, the last one is, for example, if I have probability that x is equal to 10. This also can be done by continuity correction, or we can change it with continuity correction. So remember from the binomial distribution when I said, oh, you can find this value by using the probability mass function equation or the calculator, but you can also find this by saying it's the probability of x is less than or equal to 9 minus the probability that x is less than or equal to 8, like this. This can also be found out by this. And so if this is the case, if I was to do continuity correction, this is actually going to be between 9.5 and 10.5, okay? So this is how we do continuity correction for when we have x is equal to some value. This continuity correction method takes a bit of practice, but this is a crucial step when we're trying to find certain probabilities. Alright, let's try this question 4. So with a random variable x, binomially distributed n is 100, p is 0.6, use a suitable approximation to estimate these values. So n is large, p is close to 0.5, so we can approximate. So first things first, we need to find our mu and sigma values. Remember, mu, the mean was np, right? So it's going to be 100 times p, which is 0.6, so therefore it's going to be 60. And sigma squared was np times 1 minus p. It's going to be 100 times by 0.6 times by 1 minus 0.6, which will give us 24. So therefore, if we were to approximate to a normal distribution, we would have a mean of 60 and a variance of 24, like so. Now we can actually go back finding the question. So for part A, they're asking us to find the property that x is larger than 58. We can't find this immediately, but we have to do continuity correction at this stage. So this is a squiggly line. Or let's just make it equal to first. It's going to be probability x is greater than or equal to 59. This is bigger than 58. Now if we do continuity correction, this is equal to probability that x is larger than, has to include 59, so I have to write 58.5, like so. Now I can use a calculator with mean 60 and variance 24 to find this value here, which turns out to be 0.6203, like so. So actually finding a probability is just the same as we've been doing in the previous normal distribution video, but just getting up to that stage that's slightly different now. Let's try B. So probability that it's between 60, bigger than 60 and less than or equal to 72. Once again, I change this into equals to first. So this is going to be greater than or equal to 61 and less than or equal to 72. And now I can do continuity correction. Remember, I have to include each value. So I should go down for this one, 60.5, and I should go up 0.5 for this one, 72.5, like this. Now I can plug it into a normal calculator, lower will be 60.5, upper will be 72.5, with the appropriate mean and variance values, and you should get a value of 0.454, like so. And lastly, probability that x is equal to 70. So probability that x is equal to 70, remember for an equals to, I said when we do continuity correction, we just go 0.5 down, 0.5 up. So this will be between 69.5 and less than 70.5, and then we can just plug this into the calculator again, and we get a value of 0.0102, like this. Right, let's try this question here. So we, in part A, write down the two conditions under which the normal distribution may be used as an approximation to the binomial distribution. So this is like earlier we said, right, when n is large and then p is close to 0.5. Okay, a company sells orchids of which 45% produce pink flowers. A random sample of 20 orchids is taken and X produce pink flowers. So we can say that for now it's going to be a binomial distribution with n being 20 and the probability of an orchid is 0.45. In part B, they're asking us find the probability that X is equal to 10. At the moment, we don't have to approximate, right? Because n is quite small, it's less than 50, right? So therefore, we don't have to approximate. We can just use this equation or the calculator, and you should get a value of 0.1593. Okay, second random sample of 240 orchids is taken. Use a suitable approximation, find the probability that fewer than 110 orchids produce pink flowers. So in this case, n is now large, it's greater than 50, right? So originally it would be a binomial distribution with n being 240 and p being 0.45. But because n is large, we can now approximate to a normal distribution. So we need to find the mean and variance first. So the mean value is going to be np, so 240 times 0.45, which will give us 108. Sigma squared, the variance will be np times 1 minus p. So 240 times 0.45 times by 1 minus 0.45, which will give us 59.4. So if we were to approximate to a normal distribution, x will be normally distributed with mean 108 and variance 59.4. Now we can go about answering the question. So they say, find the probability that fewer than 110 orchids produce pink flowers. So they're asking us to find probability that x is less than 110, not less than or equal to, because it's fewer than, right? So therefore, I will change this to probability that x is less than or equal to 109. Now I can do the continuity correction, which would be x is going to be less than 109.5, because I need to include 109, right? And then using the using the calculator, then I can work out this out, and you should get an answer of 0.5772. Okay, D. The probability that at least Q orchids produce flowers is 0.2. Find the value of Q. So what we can do is, the probability that X is bigger than Q, that's what they're saying, at least, right? So bigger than or equal to Q, in fact, is going to be equal to 0.2. That's what they're asking us to find, okay? Now for this, what we can do is we're trying to find Q, right? And we're still trying to approximate because Q, the n value is still large. So we're already going to have to be using this normal distribution. So what I can do instead is I can actually standardize it. Remember, standardizing is when we're trying to correct the equation, right? Using the code Z is equal to x minus mu over sigma. So first things first, I need to do continuity correction, right? Even for this. So this is now going to be equal to P is going to be, x is going to be larger than Q minus 0.5 because we need to include this point, Q value here. But now I can do this coding. So it's going to be propped as Z now, because we standardize it. There's Q minus 0.5 minus mu being now 108 over the sigma, so it's root 59.4 is equal to 0.2. And you can use if you remember from the previous video, you can use the inverse function to find what the Z value is. So Q minus 0.5 minus 108 over the root of 59.4 turns out to be 0.8416, which I can now rearrange to make Q the subject, and Q you should get a value of 115 like this. Okay, so this is basically all the different types of questions you might be able to get when we're dealing with a normal approximation. Just make sure you remember the two assumptions and make sure you understand when to do the approximations and when not to do approximations.